want to give everyone a few minutes to join us, and then we will get this started. Okay, Dave, just so you know, you are muted right now. If you would like to go ahead and unmute.
And there I am.
Hello, how are you?
I'm good. How are you?
Good. All right, Dave, the floor is yours.
Okay. Well, good morning, everyone, or afternoon, wherever you are in this country. And I want to thank everyone for joining last month, and thank you for joining again this month. And I appreciate everyone that went to our YouTube channel to have a view of last month's session. This month, I'm going to continue on the same vein of RF basics, and we're going to talk about antenna patterns and antenna behavior a little bit through this 45 minutes or an hour, however long that it takes here. So let's get started. All right. These are the five topics that we're going to broach today. We're going to understand a little bit about antenna characteristics. We're going to look at a polar chart from maybe a little bit different view than what you're used to looking at it, but it's still very simple. We're going to look at gain and isolation versus azimuth is what we're going to concentrate on here. We're going to look at the basic interaction between antennas that are co-located on a tower, and we're going to look at how to measure the performance that we might expect on a co-located system. When we put up one antenna on one tower or one rooftop, whatever it happens to be, it's very easy to take and know what we would expect out of performance out of that system. The antenna, if we remember our link budget little graphic from last month, the antenna is an integral part of the RF channel. It takes and couples the energy into the channel over the air, and of course receives the energy out of the channel, and the efficiency that it does it at is lends to its characteristics, its specifications, if you like. We all want to use these days, because of the fact that we co-locate so much equipment on towers together, that we need to ensure that we're using well-designed antennas, well-designed RF packages, if you like, and we're going to talk a little bit about the characteristics of those. Now, this is a graphic of what a couple of different types of antennas look like with the cover off. Many people have never had the cover off of a sectoral antenna on the left here. And so what we have here is we have a stack of elements. In this case, this is a left and right slant antenna. It's a 2-port. It's 65-degree antenna. You can see that there's multiple arrays. These elements that you see here are a form of a patch antenna, not unlike the patch antenna that's on the right-hand side of the slide here, but they're tuned so that that they give very particular characteristics. And when you stack them together, they are arranged in such a fashion that the impedance of the connection coming into the antenna is around 50 ohms. The elements themselves have about a 50 ohm impedance, and although out of the scope of our little tech talk today, the impedance of free space is around 52 ohms. So that's one of the reasons why that we use 50 ohms as the impedance of broadcast antennas. What we have, the more elements that we have, generally speaking, the higher the gain and the tighter the focus of the antenna. Now we have a couple of different ways of doing this that antennas that we're using often in broadband wireless here. So that we have the sector antenna on the left. We have a simple patch antenna here. I found this very easy to understand. This is on a printed circuit board, and we have the connections are a certain size and a certain shape that join the 4 patches together here. This happens to be a 5.8 gig antenna, and so it's about the size of a postage stamp, maybe a little bit smaller, and would have probably 3 or 4 or 5 dBi gain, something like that. Maybe it would be maybe it would be 0 dB gain, but nevertheless, we'll talk about that in a second here. The other antenna that I show here, it looks like a funnel, but is in fact it's a horn type of antenna or an aperture type of antenna. This type of antenna is tuned to the wavelength of the signal coming in. There's an adapter that's on the back of the antenna here that converts the coax cable input into a particular polarity that is then radiated out of the horn, and the shape of the horn actually influences the radiation pattern of the antenna. In this particular case, I'm showing a symmetrical horn that would have maybe 30 degrees beam width and 30 degrees elevation beam width, but we'll talk about that in a second. All right, let me just define antenna gain just for a second here. Antenna gain is the ratio of the energy that is being transmitted out of an antenna in its design direction as compared to the energy that would be radiated from a theoretical isotropic antenna. And the reason that an isotropic antenna is actually theoretical is, of course, because the radiating element has to be infinitely small in order for the radiation to be equal in all directions. And so that's this theoretical isotropic antenna is what all antennas are compared to. So if I have a sector antenna, for example, a 90-degree sector antenna that has about 15 dBi gain, dB isotropic. The I in the dBi stands for isotropic. So that would be 15 dB more signal in the design direction than what I would expect out of my theoretical omnidirectional isotropic antenna. Antennas all radiate in every direction from it. The graphic that I used here, I think it's a little bit chintzy, but it illustrates my point that I want to make here. There is energy. The bulk of the energy is radiated out of the antenna in the design direction. But there is other energy called side lobes in this particular case that are radiated out the sides and out the back, and it's not very symmetrical. It's kind of depending on where you are in relation to the antenna determines how much energy you can actually see from the antenna. This characteristic is really important to remember when we're building an antenna system on a tower and we're co-locating equipment together. There is energy that comes off the back of the antenna, off the sides of the antenna, out of the top of the antenna, out of the bottom of the antenna. It's just that there's more energy radiated in the direction the antenna is designed to go rather than all the other directions. So how much of that energy becomes important here as we estimate performance together. So antenna manufacturers create what's called a polar chart. This polar chart is the most important information that we have about the radiation pattern of a particular antenna. It usually is in two planes. It's in the horizontal plane, which we see on the left-hand side here. It is in the vertical plane, which we see on the right-hand side here. And this measurement, I wanted to show you what an RF anechoic chamber looks like. This anechoic chamber is designed so that it minimizes the reflections off the walls, floors, ceilings, in every direction from the antenna. This polar chart is created by measuring the signal strength that is being radiated out of an antenna at a particular level, a very low level, because the anechoic chamber is not very big. So it uses a very low level, and then at some distance away from the antenna itself, maybe it's 5 meters, 10 meters, whatever the size of the chamber happens to be, in every direction around the antenna horizontally and around the antenna vertically, the signal strength is measured. So this chart then that comes out of this is not it's not a map of the antenna pattern that it first looks like that it should be. It should be like, looks like we can just lay this on a map and there's our coverage pattern. Nope, it's not that. What it shows us is that in the direction that the antenna is designed to go, in this case 0 degrees, we have a particular signal level. As we move around this antenna and we get 30 degrees to the clockwise of the antenna, we see that the signal strength has fallen by some number of dB. This dashed line in this case of this polar chart indicates 3 dB. So antenna manufacturers spec their antennas, their width, the elevation beam width and the horizontal azimuth beam width of the antenna at the point where the energy is 3 dB less than the direction that the antenna is designed to go. Okay, so in this case, we have what looks like a 60-degree antenna because we have 3 dB less signal at 30 degrees to the clockwise, 30 degrees counterclockwise from the design azimuth of the antenna. But as we keep going around in azimuth of this antenna, we have the signal rolling off of some sort. Attenuation is increasing the farther we get away from the design direction to go. How much is it decreasing? Well, we can see that in this case, the graduations of the chart here are 5, 10, 15, 20, 25, and 30 dB to the center of the chart. So here at 60 degrees, we are down on one slant, the neg 45 slant. We are down a little bit more, no, right around the 30, 5, 10, 15 dB at the positive 45 degree polarity now out of this antenna. It's got a little bit more attenuation. So we see we're down a couple more dB than that. So the antennas aren't exactly the same. The left and the right slant in this particular case have some differences. These differences are from the perhaps from the mounting of the antenna, how close obstructions are to the antenna, near field influencers of the antenna, maybe mounting pipes, maybe that sort of thing. Maybe the differences in the two polarities are caused simply by the construction technique of the antenna. Antennas are not manufactured perfectly. They are manufactured so that the antenna will meet the specs to which it's designed to. Perfect antennas would be very, very expensive, and nobody wants to pay thousands of dollars for just a simple sector antenna. And so there's construction tolerances in those elements, as we saw in the second slide of how these are put together. In the vertical now, we do the same thing. The antenna manufacturer will do the same thing and go around the antenna in the vertical, or tip the antenna to the side and use the same test measurement and go around measuring the vertical pattern of the antenna. We can see that in this particular case, the vertical pattern is much tighter than what the horizontal pattern would be of the same antenna. The reason for that is that this arrangement, if we go back to here, this arrangement of our left and right slant elements on this antenna are taking the energy from our isotropic antenna that would be normally transmitted out of the vertical directions, the top and the bottom, and it's focusing it then in the design direction that the signal is meant to go. So in this particular case, we have a fairly narrow, maybe 6 or 7 degrees of designed beam width in the vertical direction. We have 60 degrees in the horizontal, and we have 6 or 7 or 8 or whatever it is here in the vertical. Of course, if I blew up the chart, I could measure this much more accurately, but nevertheless, we have the same 2 patterns here. We have a left slant and a right slant, and they're both slightly different, but overall, they're more or less patterns are more or less the same. You can see here that in the positive slant that we have, again, a little bit more attenuation than what we have in the negative slant, and that's probably due to construction technique of the antenna. The other thing that's important here is that we see that the main beam here of this vertical pattern is not directly at 90 degrees. If the antenna is mounted on a pipe here, straight up and down, 0 and 180 degrees, we see that the main element of the elevation is actually 1 or 2 degrees lower than what straight out to the horizon would be. So this is called electrical down tilt. That's, again, a function of how far apart these elements are when the antenna is constructed. If they're in a particular spacing, this value may be 0. If they're altered, the spacing maybe is made a little bit closer, then the differences in the phasing between the arrays will take and bend this signal down, and so then the main beam width can be bent down, and antennas can be sector antennas that we commonly use in the telecom business can have fixed down tilt of 0, or some manufacturers fix the down tilt at 2 degrees or 4 degrees. There's different manufacturers of antennas that are variable, electrically variable or mechanically variable, where the spacing between the elements is actually changed by an adjustment, and there'll be a scale on the antenna. And so if you want 3 degrees of down tilt, electrical down tilt on an antenna, you dial up with a screwdriver or an Allen key, you dial up 3 degrees down tilt or 2 degrees up tilt, or whatever it is that the RF engineer is calling for that particular installation. This particular case, now we have a couple of degrees of down tilt that is built into the antenna.
So the definitions: HPBW, you'll see in antenna manufacturers' spec sheets, the half power beam width. So that's where that's where the azimuth and elevation reach attenuation of 3 dB compared to the design direction in both. Squint, I mentioned the horizontal squint here. When we have a case of an antenna like the one that I showed in the example here a few slides back, the elements affect each other. And so the fact that all of these radiating elements are within very close proximity to each other tends to flatten out this attenuation value wider than what the half power beam width is. If we had a purely vertical or purely horizontal antenna, we would find that as we go past the half power beam width, the attenuation of the antenna rises very quickly. In a case of a dual slant antenna, for example, all of these modern antennas that support 2x2 MIMO or MU MIMO in the case of a four element antenna, the fact that all of those elements that are in close proximity to each other cause the pattern to actually flatten out, and so the roll off past the 3 dB point is much less in a dual slant antenna a multiple port dual slant antenna than it is in for example, a standard vertical or horizontal polarity sector antenna that we might be used to using in the 5 gigahertz band. So this horizontal squint is an important characteristic. What it does is for example, if I were building a four sector site to be able to use 2 frequencies in opposite directions, called a reuse 2. We'll see that in a minute here. I would take then and make use of this squint. I would use a 65-degree antenna then for a 90-degree sector. Because of the squint that I have, the attenuation at the sector edge is not nearly as drastic as what it might be if I were doing a vertical only system. All right, we have electrical down tilt. We talked about that just a little bit. That's the relationship of the elements to each other. There are really a couple of different types of antennas, sector antennas that are out there. One of them uses the antennas, the elements, I should say, are spaced so that there is no down tilt, that the beam width of the vertical beam width of the antenna is pointed right at the horizon. Then the manufacturer can change the relationship of the elements just a very slight bit, and they can electrically down tilt that pattern for 1, 2, 4 degrees, whatever. Antenna manufacturers have many different antennas with different electrical down tilt specifications, 4 being the most common. 0 and 4 are the most common. Now, there are a couple of manufacturers like Mars and a few others that make a variable down tilt antenna. It can be either a mechanical down tilt where an adjustment, a screw adjustment on the bottom of the antenna, either with a screwdriver or with an Allen key, will change the relationship of the elements inside the antenna, and you can adjust the down tilt. Also antenna manufacturers that make electrical down tilt antennas like this also make them so that they're motorized, they're remote control. And it can be that that down tilt is then varied by a controller that would be in the site. These antennas, of course, are much more expensive than just a fixed tilt antenna, but nevertheless, there's use for them. In the fixed broadband world, not so much, but in the cellular world, in urban environments, variable down tilt antennas are used quite often. The front to back ratio, we talked about that. That's the difference in the ratio of the attenuation between the design direction and exactly the opposite direction, so 180 degrees azimuth. Typically, sector antennas range from 20, 22 dB front to back ratio up to 30, 32, 34, something like that. Dishes, which are essentially horns with reflectors, horn type antennas with reflectors. Parabolic dishes will have a front to back ratio maybe in the 35 or 38 or 40 dB, something like that. So cross polarization is important in the design, but it's not that important in the application of the antenna. The cross polarization value at the bore site is the difference between the gains of two polarities that might be transmitted. In our case here, we see that we have, of course, left slant and right slant, or negative 45 and positive 45 degree slants. And we have some cross polarization value because of the fact that the left and right slants attenuation values are slightly different as we go around the both the horizontal and the vertical patterns. So this antenna would have a cross polarization value. The higher the quality the antenna is, the lower that value is. And then the second step of this cross polarization ratio would be what the value is at the half power beam width. And so we see here that that we do have some difference between the two, then a little bit more difference. You can see the width of the pen here, difference between the red trace and the blue trace at the half power beam width. So manufacturers will give us this value. And again, the lower the value, the better the antenna. So more graphically then, let's take a look at this thing, this typical pattern up close. This happens to be a KP performance antenna, by the way. It's a 4-port, 65-degree dual slant sector antenna that we have taking the measurements from. So we have here the azimuth pattern of this antenna, the left and right slant again. Remember and so when we look at it up closer here, we see that the cross polarization is nearly zero at the azimuth, the design azimuth. And as we get out to the 30-degree half power beam width points, we see that there is some, not bad, and so the cross polarization value of this antenna is actually quite low. What I want to point out here, though, is that this is the important point of this slide. When I relate it back to my link budget now, my link budget, if you remember, was the energy that's being transmitted from, in the downlink, was the energy being transmitted from my base station being received out in the field at my subscriber unit. The uplink link budget is exactly the opposite. It's the energy being transmitted from the subscriber unit out in the field being received by the base station itself here at the tower. So we're going to talk about the downlink now. Since the graphic here, we're going to talk about the energy being radiated out towards the subscriber equipment. If I were to be directly in front of this antenna at 1 kilometer away, this were let's say a 3 gigahertz system, let's say a 3650 system, I would expect that I would have about 104 or so dB of free space loss between my antenna at the base station and my CPE device. That's the minimum loss that I would expect over 1 kilometer. I can have more loss than that if I have some non-line of sight characteristics, if I'm hiding behind some trees or whatever the case, but let's assume it's line of sight just for our little demonstration right here. Now, in this particular case, if I went out here, measured my signal at my 1 kilometer range, I might find that I have a minus 65 RSSI, 65 dBm RSSI. Okay, that's great. So at that particular point, if I moved 30 degrees in a counterclockwise direction from my tower site, I would estimate then that my signal at that point, my RSSI would be 3 dB lower here than it is here. If I go out another 30 degrees from this, now I'm 60 degrees away from my azimuth. Even though my antenna may not be designed for that, I am still going to receive my signal at a minus 75 at that particular case. My numbers here, I used minus 60 here in the slide, and so at the 3 dB point, I would be at minus 63. At the 60 degree point away from the antenna, I would be somewhere around a minus 70. And then as I kept on going here towards 90 degrees, you can see that I would be a minus 25 less than my value here. So if my value were 65 at this point, I would be minus 90 out at that point. So I'm still receiving this energy. This is the important thing. I'm still receiving this energy out here. It's just that it is less than what I would expect if my CPE were right in front of the antenna. This is an important fact. Just we'll talk more about this in a minute. Now, one other thing that I want to point out with sector antennas that are mounted is that in this particular case, if I'm out at 90 degrees here and I'm seeing 25 or whatever less than the dBm less than what I would expect at the same distance on the 0 degree azimuth of the antenna. When I move all the way around now from this point, from actually past 90 degrees here, all the way through the 180 degree azimuth back up to the positive 90 degree azimuth in this particular case, I would expect about the same level of signal. So if I were at this minus 60 point here at the 0 degree azimuth, just follow me here, at some point beyond minus 90, I'm going to hit minus 90 dBm here. I'm going to be 30 dB less than this signal here. My front to back ratio of this antenna is 30 dB. So I will be minus 90, 90, 90, all the way around. The minus 150 will be minus 90. I will be, again, and when I reach the 90 degree point away from that antenna, my signal will start to rise. And at that point, I might be minus 25. And so then I'll be minus 85 and so on and so forth as I get back to the design azimuth of the antenna again. So this is an important fact to remember here, is that I am radiating energy in every direction from this site. And it's, the energy is much better in the direction that I want to go to, but I am radiating in every direction. So let's apply this now. So I have a tower here that I put 4 identical sectors on. So I've used 4 of these KP antennas at 0, 90, 180, and 270 degrees azimuth on my tower site. Fine. Let's say I have a subscriber who is located at minus 60 degrees away from the tower site. So in this case, I would expect this CPE to connect to my west sector, right? Minus 90 degree sector here at this point. I would expect that that signal then, if he were 1 kilometer away, and from our example on the previous slide, I would expect my signal strength to be at that point about a minus 63 or minus 64, something like that, because I am at the half power beam width of this western antenna. However, if I were to take and switch sectors to the north facing sector, I would only see 7 dB difference between the signal that I would receive from the north sector compared to the signal that I'm receiving from the west sector. So let's think about that for a minute. So 7 dB. Okay. If something were to happen to this sector, I could allow this CPE to join the north sector. And if the west sector were to go off the air for some reason, that CPE that's out here at the 60 degrees could join the north sector. And probably if we had the high enough minimum installation value, he would join the sector and he would be perfectly happy coming off of this sector. So this is why in some systems, such as an LTE system, when the CPE makes a decision to join a sector, if there was an anomaly going on right at this moment with the west sector, and the north sector was actually a better quality signal than what the west sector is, maybe because it's a little less signal strength or something, the CPE might want to join the north. It might be perfectly happy joining the north sector, and even though it's pointed at the west sector, it might want to choose that north sector and would be quite happy connected to that sector. Then if the problem were to clear up, let's say that let's say we change the radio in the west sector, or adjust the power level or something. We do something to the west sector to bring it into spec again. If the CPE has a rescan function, it would then join the west sector because that would be its better sector. But if the CPE does not have, then you can fix this sector up, but the CPE is still going to be connected to the wrong sector. It's going to be connected to the north sector. My next slide is going to deal with what happens in the uplink with this very arrangement. But in the downlink here, what we see is that the CPE is going to have a slightly lower RSSI than what it would have if it were connected to the correct sector. Why is this important to know that this phenomena occurs out in the field? And how do we know? So if we have our sectors, individually named or numbered, or whatever the case, then we're going to see in the CPE itself, if we log into that CPE, we're going to see that it's connected to the north sector. But from a performance standpoint, I need to know if I'm getting the signal at this CPE location that I expect I should be. And so if I do a link budget, assuming that I'm connected to the west sector, I would come up with a particular value that will be higher, I should say, than what I am actually operating at now. If I do a link budget from the north sector, taking this azimuth into account, I would then be able to reconcile this RSSI value that I'm seeing at the CPE compared to what I would expect to see on the sector that I really wanted to connect to. This sector that the west sector in this case is called the best serving sector, because of course the signal strength should be better to the CPE location than it would be from the north. If this were at 30 degrees now, if this CPE were at 30 degrees, then the north sector would be the best serving sector, but I would still be able to receive the west sector at that CPE location. So it's important here. Important thing here is that this channel plan be correct. This channel plan needs to be, non-overlapping. It needs to, have enough separation in here and probably be GPS synchronized so that when my CPE wants to connect to or I want the CPE to connect to the west sector, that in fact it is going to connect to the west sector, not connect to the north sector. It might be possible, if the CPE is close enough to the base station site, that it could connect to the south sector or the east sector. And again, be perfectly happy joining those, because remember that the signal, there is east sector energy that goes out towards the west. There is south sector energy that goes up towards the north and the west and the east. So we have this arrangement of energy that's being radiated off of this tower. And so this means then that I need to be able to take, and when I put a CPE out here on the west sector, I need to know that that CPE is going to stay on the west sector. So different manufacturers, of course, have different ways of doing this. With Cambium, it's the colors. With others, it might be the MAC address. With LTE equipment, it would be the PCI value. You would do cell locking on this to lock it to that particular sector. All right. One of the other facets of characteristics, I should say, of broadband equipment today is the fact that the automatic transmit power control is almost always, the uplink is always automatically transmit, the ATPC, automatic transmit power control, works in the uplink. Tripping over my words here, excuse me. So why is that? All right, so if I have a CPE that's in close, let's use the west sector here again as my example. If I have a CPE that's in very close and I have a small amount of path loss, maybe only 70 dB instead of 104 like it would be at a kilometer, I have 70 or 60 or 70 dB of path loss in here. My receiver, if it receives this really strong signal from a close CPE and then this weaker signal from a CPE farther away, and maybe even a weaker signal from a CPE farther than that, the receiver here would have a hard time to decode the data from these. It'll have a hard time to adjust itself to the energy that's coming from these various CPE at various distances. So the way the systems look after this now, especially OFDM-based systems in general, which is now, you know, all of Wi-Fi 6 systems and of course Cambium's 450s and all LTE networks are all OFDM-based, right? So these guys, all of these systems are going to take and adjust the transmit power at the CPE so that the near CPE, the medium distance CPE, and the far CPE all arrive at the same energy level at the base station. That's the goal. That's what the design would be. The perfect design would be that near in CPE might have a signal strength, or I mean a transmit power of maybe, I don't know, let's say plus 9 dBm. This one farther out might have a transmit power of plus 14 dBm or 16 or something like that. And the CPE that's at the very edge of the network might be at plus 22 or something like that. So anyway, the end result of this is that those three signals, when they're transmitting towards the base station, make the receiver, this West receiver that they're all going to be connected to, they look the same as far as the level goes to this receiver. Easier then to take and decode the data. What happens here in our case where we are not on the best serving sector any longer? Now, because the antenna attenuation holds true in both directions here now, my best serving sector at the 60-degree point is I have 3 dB less gain than I would at the minus 90, or 3 dB attenuation at that point. But if I'm connected to the north sector, now that attenuation, instead of being 3, is now 7 or 8, whatever this number happens to be here. Let's say 8 dB compared to the 3 dB here. And so at that point, if I'm going to connect to the north sector from this CPE out here, my transmit power of this CPE will go up 5 dB compared to the transmit power that I would see if I were connected to the best serving sector. So if I'm on the best serving sector, my transmit power from my CPEs are as low as they can be. So I'm generating the least amount of RF noise, and I'm causing the least amount of what's called adjacent channel interference here to my sectors that are co-located on the tower. If this CPE joins the north sector, or heaven forbid, it joins the west or the south or the east sector, then the transmit power of that CPE will be turned up to maximum in order to take and arrive at the same level at, let's say, this south sector as what all my CPE that are actually connected to the south sector would arrive at that level. And so this might drive the power up to the maximum. Now, whoops, let me back up here. Just one more thing I want to point out here. At this point, if that happens, if this CPE then connects to this sector for some reason, and even though the downlink signal is very poor, the uplink signal, the automatic transmit power will be screaming to try to make sure that the level is proper at the receiver. At that moment in time, this CPE becomes interference to the north, and perhaps even interference to the sector it's designed to be, going to the west. And so this ends up being a situation where if I have enough of this going on around my tower site, I will end up reducing the performance of my tower to a point where all right. I want to talk a little minute here about antenna tilt. I'm sure that there'll be some questions about best serving sector. If you have some questions, feel free to jot me an email, send it to marketing@mbsiwave.com, and I'll be happy to answer any questions that you might have regarding this best serving sector phenomena here and the relationship between sectors that we have. We need to take and spend time with this because it's really important to the operation of your network. All right. So finally here, we're getting close to the end. I want to talk a little bit about a down tilt just for a second here. So in the case of our antenna here, using the same pattern, we see that we have some electrical down tilt. In this case, we have 3 degrees of electrical down tilt according to our little polar chart here. So good to know. So when I take and figure out where I want, how much down tilt that I need, I use a set of calculations here. Antenna has an upper beam width, of course, a lower angle for the elevation beam width, and I want to take and put the main lobe kind of in the middle of the area where I want coverage. Typically, that's the case. And so, using these formulas, I can take then and calculate what the antenna down tilt should be for a particular site. Tools like Cambium's link planner, you press a button and it does it for you. It calculates what the down tilt should be for the CPE that are inside that are connected to a particular sector, and then adjusts that tilt for the maximum performance for the CPE that are connected to that sector automatically. Other tools do the same thing, but if you have to do it by hand, this is the way to do it with a spreadsheet. So some typical calculation results here, using this particular antenna that I've got here, because of the electrical down tilt. If I set my mechanical tilt at 0, find the upper edge of my antenna is over the horizon. My lower edge of the lower main lobe is at about 0.6 of a kilometer away from the site. And then as I increase the tilt, you see that my lower edge actually gets closer and closer to the site. And at some point in time, at 4 degrees here, I see that I'm not the upper edge of my beam width is not over the horizon anymore, but it's at about 5 kilometers. And so this is the effect of down tilt as we take and bring it down. Now, if I were planning to have my sector cover, let's say 10 kilometers, which is really kind of typical, right? I want a 6 mile, I want a 6 mile coverage range or 10 kilometer coverage. So in this case, I might want to take and set my my antenna tilt, my mechanical tilt, then to let's say 2 degrees, something like that. So I got 3 degrees that are built in, and I might add 1 or 2 degrees to that if I wanted to, and I would put myself somewhere in this 3 to 4 degrees total elevation down tilt in order to take and put the most signal that the range that I want to put it in. Again, it's a little bit out of scope for here, but I just wanted to show you that this is the case. Now, if I absolutely wanted to get the best range out of this, let's suppose my tower is low. Let's suppose I'm using a 100-foot tower, and let's suppose that my CPE are 25 feet off the ground for the majority of my households. If I go back to my calculation here, you see that I have a height of the tower, I have a height of my CPE, and then the relationship to this, the angle that I need is actually tangent of the relationship between the distance and the difference in the height of the tower to the CPE. So what that means then is that the lower my tower is, the less my tilt happens to be. And it may be that in a case of where my base station height here is say 100 feet or less, and my CPE height is 25 feet, then perhaps I have to take this antenna that has electrical down tilt, and I might actually have to tilt it up in order to put this so that my electrical tilt actually comes out at the horizon at 90 degrees in order to get to the CPE that I need to. So just this is important from the point of view that I may need to use an antenna that has electrical down tilt. I may need to use up tilt in order to take and compensate for low heights of my tower and high heights of my CPE. All right, just another couple minutes here. All right, so minimum performance requirements. We talked about a little bit about this last month too. We talked about the minimum that it takes to reach QAM 256 and QAM 64, and the table in the last month, I went down to QAM 16 and QPSK as well. So, but in order to take and reach these kind of performance values, the antennas have to provide enough isolation. So the rule of thumb is that on 3 sectors per site, I want to use 90-degree half-power beamwidth antennas spaced at 120 degrees. On a 4-sector site, I want to use 65-degree half-power beamwidth antennas spaced at 90 degrees. If I want to put up 6 sectors, and I have only 2 frequencies that I can use, I need to make sure my arrangement is F1, F2, F1, F2, F1, F2 around my 6 sectors, then I need to use 33-degree half-power beamwidth antennas spaced at 60 degrees. If I have 3 frequencies that I can use, then I can relax that spec a little bit, and I can use 45-degree antennas spaced at 60 degrees, and then I can take and deploy channel 1, channel 2, channel 3, channel 1, channel 2, channel 3. So channel 1s are back-to-back, 2s are back-to-back, and 3s are back-to-back in our 6-sector arrangement. All right, so my recommendations. Calculate the link budget for the maximum range and for the minimum expected data rate and performance. The maximum range needs to be always less than the RF horizon, whatever that is. Going out to the RF horizon, you might have a connection then that is definitely connectable to your base station, but the data rate that you can achieve at that connection may be way less than the minimum that you want to serve that customer with. Second thing is calculate the antenna tilt required to reach that range using the height of land, the height of the tower, and the height of the CPE. You come up with those values, and all of the internet, all of the tower, the antenna tilt calculators that are on the internet all do the same, basically the same function. So you can take and use one of those to figure out what your tilt needs to be for that sector if you're doing it by hand. And then the mechanical tilt required is equal to the tilt required for the performance you need minus any electrical tilt that's built into the antenna. So if you bought antennas that have 4 degrees of electrical down tilt and you require 2 degrees of tilt for performance, that means that you have to up tilt that antenna by 2 degrees. And mechanically, in order to have the electrical tilt at the correct value. So as I mentioned before, any questions that you have, any topics that you want to have me discuss in the upcoming Tech Talks, please send an email to marketing@mbsiwave.com, and I'll be more than happy to take and address your questions and work in any suggestions for topics that you might have for Tech Talk here. In the next little while, I plan to stay on this link budget bandwagon for a little bit. There's some deeper subjects here that we need to talk about in relation to things like MIMO, for example, and perhaps beamforming and other things that are happening now in broadband wireless equipment as a matter of fact rather than as something special. And so I need to, we'll be discussing those topics over the next few months here. But as I mentioned, any topic that you might want to have me discuss, then feel free to send an email. I really appreciate your time today. Thank you very much.
Thank you so much, Dave. And we don't have any questions at this time, so we will let everybody go.
All right.
Thank you. Looking forward to the next one.
Have a good day. See you.